Okay, so let's discuss finite micellization. So in the last lecture, we determined that the expression we had for the number of amphifiles in an aggregate of size n was given by n over gamma n, a1e to the alpha to the n times e to the minus alpha 1 minus p. And so we said that for the case of spherical aggregates, this reduced to xn being equal to n over gamma n, a1 e to the alpha times e to the minus alpha, I'm sorry, this is n to the 1 minus p, e to the minus alpha n to the 2/3. And we said that since a1 e to the alpha has to be capped out at 1, right, even if this goes to a1 equals e to the minus alpha, so 1, this is still going to go to 0 as n goes to infinity. So if this was the energy by which, or the way the energy increased for the amphifiles in the aggregates, or the energy decreased for the, or increased for the energies in the amphifiles in the aggregates as they got smaller, then this would not produce aggregates of a finite size. So now there's an exception to this, and that's the case where either we don't have this simple relationship that we had derived between the chemical potential of the amphiphile and the number of amphiphiles in the aggregate, or there's the case where p equals 1. So p equals 1 is an interesting case because in that case we know that we can write xn as n over gamma n, a1 e to the alpha to the n, and here we get 1 minus 1, so this we just get e to the minus alpha n to the 0, which is of course 1. Okay, so in that case, for small n, we can see that xn is going to go like n, so it's going to increase with the size of the aggregate. But when n gets large, it goes like, or we know that the a1 e to the alpha to the n term dominates. And so xn then has to go to 0. So since it's increasing at small n and going to 0 at large n, we think there must be a peak in the middle, and that peak should tell us what the peak typical size of an aggregate is, what the peak size of the aggregate is. So what we want to do is take into account something that we haven't been taking into account so far. Let's take into account the finite amount of amplifier. So we want to say that the sum, if we take the sum over all possible monomers in all possible aggregates and add up the mole fraction of all of those, that has to equal 1, just by the definition of mole fraction. And we can write that as the sum, or we can pull out in front the things that don't depend on n, so the e to the minus alpha we can certainly pull out front, and then we have sum n equals 0 to infinity of n, and we're going to assume gamma n is just 1. We're going to be very simple and say that the activity coefficient is just 1. So here then we'd have n, and then we'd have a1 e to the alpha to the n. And if we look at this, it has a very peculiar form, and there's an identity that sum of n equals 1 to infinity of nx to the n is equal to x over 1 minus x squared. So we can write this as 1 equals e to the minus alpha, a1 e to the alpha over 1 minus a1 e to the alpha squared. And that's the same as saying, right, 1 minus 2a1 e to the alpha plus a1 squared e to the 2 alpha is equal to a1. And so then we could bring the a1 onto the other side. We get 1 minus 2 e to the alpha plus 1 plus e to the 2 alpha a1 squared is equal to 0. And now we can solve for a1. When we solve for a1, we get an expression that looks like a1 equals 1 plus 2 e to the alpha. And then we have plus minus, because it's the quadratic equation, right? 1 plus 4 e to the alpha over 2 e to the 2 alpha. And we can see that since a1 has to be positive and less than 1, that the negative is the correct sign. And if we assume e to the alpha is much greater than 1, we get a1 is approximately 1 plus 2 e to the alpha minus 2 e to the alpha over 2 over 2 e to the 2 alpha. Or in other words, a1 is approximately e to the minus alpha times 1 minus e to the minus alpha over 2. Okay, so this gives us an expression for the number of monomers in an aggregate of size n, right? Because we have an expression now for a1, so we can write this as n times 1 minus e to the alpha over 2 to the nth power e to the minus alpha. Okay. And we can plot that. So we could plot xn as a function of n. And what we'll find is that for small n, this goes like linear in n. So we have some linear function. And then it actually peaks at some point and then starts to go down, right? For large n, this is less than 1 and this starts to dominate again. And if we want to know the peak, of course, what we do is we take the derivative of xn with respect to n and we ask when is that equal to 0, right? And so that gives us an expression that's like 1 minus e to the minus alpha over 2 to the n e to the minus alpha plus n times natural log of 1 minus e to the minus alpha over 2 times 1 minus e to the minus alpha over 2 to the n e to the minus alpha. And when we solve for that to be 0, we get that 1 is equal to n minus n natural log 1 minus e to the minus alpha over 2, which we can say is approximately, in the small, when this is small, equal to plus n e to the minus alpha over 2. So, so that will be true when n is equal to e to the alpha over 2. So this maximum, let's call this m, is equal to e to the alpha over 2. And that's our most probable or maximum maximum probability size of a micelle. Okay, so we can see that in certain cases, for certain choices of how the energy of a amphiphile in an aggregate varies with size, you can get a peak size, and it can pick out, the system itself can end up picking out a size of aggregates that one would have in that system.